Alejo, I think you should start now because if not, we are going to be out of time.
Yep. So, welcome everyone. The purpose of this workshop, if we could call it that, is just to get together and do like the jazz musicians, like a jam, just, share some thoughts on the particular topic of recursivity. For people like me, who work in computer science, programming, and so on, recursivity, it's like, your daily driver, let's say. But for people from, uh, let's say, another lines of work, isn't something like really intuitive or simple to understand. But to simplify it at a really high level, we could say that something is recursive when it uses itself to do a repetitive task. Let's say that the simplest recursivity could be when you take a single number and you power it to with another number. Let's say 2 to the power of 2, you multiply 2 by 2 by 2 by 2, and that amount of times as the small number indicates, okay? So I have, the other day I was searching YouTube, I know, really productive from me. Uh, and I saw a video from this guy, Derek, in a channel who's called, that's called Veritasium. A really interesting mathematical problem he was taking a look to in that particular video. The problem, it's called 3x
X
plus
plus
1.
1.
That one, yeah, you saw the video, right? So it's really like, from the mathematical point of view, they are trying to see if applying this particular formula, you have some group of numbers that go into an infinite loop. So, but let's do a really a quick example. The rules are really basic. If you have a number, and a number with an integer number, okay? If the number is even, you divide it by 2. And to that result, you take a look again, and if the number is even, you divide it by 2, and so on. But if the number is odd, you multiply it by 3 and add 1, okay? So do a quick example. If you have, let's say, 5, it's odd, so you have to multiply it by 3, which is 15, plus 1 is 16, right? Please feel free to participate because maybe
Yes.
I get something wrong, okay? 16 is even, so we divide by 2, which is 8. 8 is even, divided by 2 is 4. 4 divided, it's even, divided 2, 2, 1. And then take a look to this. 1 is odd, so 1 times 3 is 3, plus 1 is 4. 4 is even, so divided by 2 is 2, and 2 divided by 2 is 1. And then 1 times 3 plus 1 is 4, 2, 1, 4, 2, 1. You get caught here in an infinite loop. And so far, all people have tried with really giant numbers, and all the numbers end in this particular recursive loop. So I was taking a look to the graphical representation of the algorithm, and I saw that it resembled to some nature formations. You can graph it, you can draw it like a graph, and it looks like a tree. So in my mind, I say, okay, I will make a script to try to do a curve representing, the progression of the numbers. So for that, I will here create a script. I don't know if you can see here the editor, or I need to show, change the.
No, it's possible. Yeah, we see it.
Okay, yeah, because Linux Grasshopper, they use like a lot of different windows, so sometimes you have problems when you are sharing your screen. So this is C#, and basically what we need to do is to do a particular function, okay, which calls itself over and over and over until we get the result we are getting. So here we can make the recursive function. We could call it whatever we want, but let's call it a recursive for obvious reason. Here we need to specify what we will be returning. I want to build a curve, but in order to build a curve, the only thing I need is just a list of points, okay? So I will use a linked list because I like linked list, and the generics management of C# is horrible, but don't tell them that, of points. Okay, and here, what I need to do, it is something like, just we need to equal the object. A in this case is the thing that we are going to return. It's equal to recursive, which is our. So the idea here is we will call this function with a number. I'm using my notebook's trackpad, so sorry if I look like a 2-year-old with my mouse, okay? Let's define a number between 1 and 100. We can connect this to the first parameter. We will say to this particular parameter, it is an integer, okay? And by number, we can call it. So here, we know that we need the number, to apply the 3x plus 1 rule. Here, we will receive the number. And then we can start. So we can ask if the number is even. This means the number is even. On the contrary, the number will be odd, right? So if the number is even, we need to divide that number by 2. What we can do here, number equals number divided by 2. On the contrary, if the number is odd, number equals to number times 3, okay? Plus. Okay, so we have like the basics of our algorithm, but now we need like a graphical representation. We are not drawing here. So what we can do, we need the list to add the numbers. But if I define the list here, the recursive nature of this algorithm will create a new list each time I process a new number. So it doesn't make any kind of sense. So I need a list here. We can create here a linked list of point 3D, and we will call it here list. Okay. So once we identified if the number is odd or is even, and we calculate the next number, we need to add it list, right? So we can here list dot the last. Here we can create a point, new point. And here we can start playing with the coordinates of the points. As an exercise, let's say for the x coordinate, I want to put the number. For the y, exactly the same. But for the z, if I use the same, maybe I will get in trouble. So I am thinking that for each number, I want to have like a level. So I need to know in which level I am. So we will define some depth, okay? Which will start in 0, and then we will be incrementing that number. Let's put here depth times, okay? So far, I am running out of time because we are a lot of people. So what I will do is I will copy the algorithm I already have here. And I will explain it and I will show you the results. Sorry, I have only 10 minutes. So if of course it doesn't exist, we need here to create a new parameter called height. Int, and we can define that for, I don't know, between 1 and 100. If we connect this, and then for this result, we create interpolation. We add the vertex. We see something like this. If we take a look to the number, we started then with 5, right? Or 6. You can see here the little curve, like a little vine or twine, okay? And if you start incrementing this number, you will see how the algorithm starts to change and connect the dots. This is because if you take a look here, the algorithm is calling itself every time that the number isn't trapped in that original loop that we described, which is between 1 and 4. So you can find this algorithm in a Sharp folder, not only this one, but the ones that the guys will show next. This is really, you know, more like a thought experiment than an actual, you know, useful algorithm, because take a look to this curve. It isn't something, you know, useful, but it's really interesting and simple to wrap your head around how recursivity works. If you have some time and you want, you know, to play with some parameters, maybe the angle of the points relative to one particular point, the origin or the original number, I assure you, you can create some cool structures like I don't know, some branches, trees, and so on. So I try to maintain it really simple and you know, ground it into a really good video. I recommend that you take a look to Veritasium's 3x+1 video. And that's it from me. So now the guys will go ahead and show cooler algorithms and more beautiful things than my humble code. So thank you.
Hello, everyone. I will share my screen. For this exercise, I am using a Grasshopper that is the algorithmic editor in Visual Programming for Rhine. I have installed a plugin called Rabbit that you can find in morphocode.com. The concept of Lindenmayer system or L system was conceived by the Hungarian biologist Aristide Lindenmayer in 1968. An L system basically is a language to do a formal description of plants or a biomorphological description of natural organisms and microorganisms. So it works with a set of rules and symbols used to model the growth process of plants and another kind of fractal patterns. To simulate this process, I will use the component L system and the component turtle, that is the algorithm that will interpret the rules and create the geometry. Let's see, for example, the rule F means move forward a distance L or step length that we have here and draw a line F and the alphabet that we define, for example, A, contains all those rules to create three derivations B with angles. The slash symbol means roll right A in some angle that we define here. So we can change, for example, to see this rule, a series of rules. We can see it now. And the number of generations is a recursive rule in a fractal way. For example, A will becomes AB, AB will becomes ABA, ABA will becomes AB, 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 and each letter contains a series of rules. Now we can add more generations. And change the angle, for example. And we can start firstly with the rule F. So that I'm gonna do now is constructive detail in the nodes. To make them on a 3D printer and combine them with pipes. So we cut here the lines. And we know the length of those pipes. And we can see here how many pipes we need. List length. We need 40 pipes. I will join the curves. Join the curves. And I will find the points of the nodes with a physical intersection between multiple curves. And I will gonna draw a sphere in each node. These points, and the radius can be the length of this step divided by 4, for example. Division. In 4. We have now these spheres in each node. And I will find the intersection between the lines of this and these spheres. But I need to convert them in a 3 data structure. Graph 3. You can see the difference between these data structures. This is just one list, and this is a series of lists. Now I will find the physical intersection between breadths and curves. We have the breadths here in a data structure and the curves. I will plot them. You can see now the points. And I will draw a new lines, but just in each node. but I need to clean this data structure because we have many empty lists. We can do it with clean tree, remove empty data. This is the tree, the points. The empty data is false. I will put in true. Napoleon operation in true. We have now just the points. And I will find the closest points in each node. Closest points. This is the cloud of points. And this is the points of each node. And I need to find 4 points. Now we have 1, 2, 3, and 4 points. And the central point of the node. I will turn it off. I will draw 4 lines with these points. So I will call the component line. The starting point is the central points, but I need to convert in a tree data structure, graph tree. And the closest points in the end of the points. I have now 4 lines. It's a pace. I will take each line with a list item. This is the list, and I have 1, 2, 3, and 4 lines. One, two, three, and 4 lines. In each line, I will do a pipe, and the radius can be, I don't know, pipes. in millimeters. For example, maximum 15 millimeters. Radio. The internal pipe, for example, I will put in 5 millimeters. And I will do an offset of this surface, the pipe surface, with the thickness of the node. For example, can be with a slider, maximum 7, I don't know. And for example, the thickness can be 4 millimeters. Node thickness. And I will do a solid difference, a Boolean operation between the external pipe with the internal pipe. But I need to cap the holes firstly. Cap holes, internal pipe, and external pipe. Solid difference. Solid difference between the external pipe with the internal pipe. And I'm gonna do with each line. Line 2. Line 3 with the same process. And line 4. And I will group them. So these objects. And now I'm gonna draw the other pipes. Pipe of all curves. With the pipe radius. And now I'm gonna put it in different colors. Swatch color, custom preview. So this geometry, I wanna see it in one color. I will put the caps flat. And another color for the nodes. For example, blue. Now let's change the parameters, for example, egg generations. And a different angle, for example. Thank you, that's it. I will try to do in a future with a planar elements. Who can be next? David.
Muy bien, José. Muy interesante. Hello, everyone. I try to explain in Spanish because my English is so bad. Voy a intentar explicar o trabajar con los comandos nativos de Grasshopper. Voy a compartir mi pantalla. ¿Se ve mi pantalla ahí?
Sí.
Ok. Como dijo José y Alejo, los sistemas recursivos y los L-systems son funciones que se llaman a sí mismas y generan unos loops o unos bucles. Al llamarse a sí mismos, al recurrir a la misma función una y otra vez, se producen formas complejas a partir de reglas simples. Los L-systems son una muestra de cómo, a partir de un iniciador, puedo escribir aquí, perdón, cómo a partir de un iniciador yo puedo producir con una regla sencilla transformaciones que generan geometrías complejas, ¿cierto? Entonces yo puedo tener este iniciador y después repitiendo el mismo procedimiento. Es que esto, ya sé qué es lo que pasa. Repitiendo el mismo procedimiento, puedo generar formas que se van volviendo complejas. ¿Ok? Esto porque se recurre a un loop. Esta es la base de los L-systems. Un loop. Lo mismo que las funciones recurrentes. Como todos saben, en Grasshopper solo hay una dirección. Cuando yo enciendo Grasshopper, cuando yo trabajo en Grasshopper, Grasshopper solo tiene una dirección. Grasshopper es unidireccional. O sea que producir una función recurrente o un loop es imposible. Hay plugins como Rabbit, que mostró José ahora, que permite iterar o reproducir una función una y otra vez. Pero con comandos nativos de Grasshopper no es posible. Grasshopper solo tiene una dirección. ¿Ok? Pero Grasshopper tiene una posibilidad y es que cuando yo dibujo dentro de Grasshopper, cada vez que opero sobre una forma geométrica se genera una instancia de la forma geométrica. Cada vez que yo cada vez que yo genero una operación sobre una geometría, repito esa geometría como una copia. Y además yo puedo recoger esa copia y utilizarla como dato de entrada para otra función. Entonces yo voy a tratar de utilizar esa idea de utilizar las copias o las instancias de los elementos geométricos en Grasshopper para producir una función recursiva o recurrente, un sistema tipo L, solo con comandos nativos. Esa es mi intención. Lo primero que voy a hacer es voy a producir unos puntos para producir el iniciador. La rama, el primer copo, que es el que va a producir al que se le va a generar la transformación. Entonces lo primero que voy a hacer es voy a trabajar con unos puntos. Vamos a copiar. Vamos a hacer 4 puntos. Uno que esté en el origen. Y otros que se puedan mover entre los negativos y positivos de las coordenadas. ¿Ok? Tengo este punto, tengo el origen y voy a construir otros 2 puntos distintos. Con los cuales voy a producir el iniciador. Después voy a generar una línea entre ellos. Curvas, líneas. Y voy a producir una línea que una cada uno de esos puntos con el origen y tengo mi iniciador. Este va a ser mi iniciador. La idea es que yo voy a generar una transformación geométrica sobre el iniciador y esa transformación geométrica, aprovechando lo que dije ahora, que Grasshopper mantiene una instancia o una copia del objeto. Cada que yo haga una transformación voy a volver recurrente esa transformación. ¿Ok? La transformación que voy a realizar. Esto aquí. Si yo abro esto, se ve una tabletica de bambú, ¿no? Andrés. ¿O solo
No,
se ve
no
mi
se ve.
Grasshopper?
Solo
se
se
ve
ve
Grasshopper.
Grasshopper, sí.
Ok, vale. Entonces, la transformación que yo voy a generar es una orientación de este trío de líneas. La voy a ubicar aquí, la voy a ubicar aquí, la voy a ubicar aquí. ¿Ok? Para eso, voy a agrupar estas líneas. Las voy a convertir en un grupo. Y ese grupo es el que voy a orientar en cada uno de los extremos del iniciador. ¿Ok? Busco una operación que se llama orientación. Está aquí. Este orientar me pide la geometría que voy a orientar. Me pide un punto inicial de referencia. Voy a tomar como punto de referencia el origen. Después me pregunta una dirección de orientación, yo voy a asumir el eje Z como la dirección base de orientación y después me pide los puntos target donde yo voy a dirigir la orientación. Yo voy a agrupar estos puntos en una sola lista. Para poner ahí. ¿Okay? Si yo repitiera esta operación, muchas veces tendría un sistema L a partir de una transformación básica que puedo condicionar a partir, o que puedo, moviendo los parámetros, restringir la posición del iniciador. ¿Ok? Si se dan cuenta todos, las ramas están orientadas a parte del vector Z. Yo puedo asumir además que cada línea es un vector ahora normal o de orientación y puedo asumir que cada línea es un vector con el cual se pueden orientar las nuevas transformaciones. Vamos a hacer eso. Vamos a utilizar un vector entre dos puntos y vamos a producir un vector entre cada uno de estos vector unitario que me mantenga la dirección y ese vector lo voy a asumir como la dirección a la cual van a estar orientadas cada una de las nuevas transformaciones. Ok. Vale. Incluso yo podría manipular este vector para que cuando se haga la nueva orientación yo genere una reducción en la escala. Entonces vamos a ir a vectores, vector, amplitud, y puedo, modificando la amplitud de estos vectores, generar una reducción en la escala en la nueva operación. ¿Cierto? Si yo repito esta operación una y otra vez, entonces tendré un sistema L. Vamos a hacerlo. Vamos a ir a transformaciones útiles. Aquí hay uno que se llama transformar. Y yo puedo copiar todos los datos de esta transformación y utilizar estos elementos como unidades de entrada y generar ahora una nueva iteración. Es decir, la recursividad, el loop, la iteración se va a hacer no generando un retroceso en la llamada a la función, sino utilizando la instancia que genera Grasshopper. Y yo podría copiar esto. Y voy produciendo. Con una transformación sencilla, una forma bastante compleja. Solamente llevo 1, 2, 3, 4, 5 generaciones y ya tengo un árbol que es bastante parecido a un sistema L. Bueno, era una pequeña muestra de cómo, aprovechando las cualidades de Grasshopper, podríamos generar un sistema L básico. No sé si alguien tenga alguna pregunta. Las definiciones, we can share the definitions for the people, ¿no?
Gracias.
Let me share the link into chat.
Okay, so I guess it's my turn. So
Yes.
I'm going to share my screen. Okay. Are you seeing my screen now, right?
Yes.
Okay, my name is Andres Obregon. I am an architect from Medellin, Colombia, and right now I am teaching it at UDEM University in Mexico. Maybe you know this is the first time we meet together as a group to do a workshop, so I am very glad about that. We have this idea to make a lab focus on architecture, design, and computation. And what I'm going to show you is as well using Grasshopper and the CSharp language. So the code I'm going to present to you is on GitHub. I share here the link if you want to download this file. Is the version 3, the recursion function. So when I get started to get interested about this kind of behavior in programming, my point of the part was the amazing examples in nature and how to approach this morphology. And there are many examples that are amazing. And when we start to think how we code this, my point of the part was to study the book by Daniel Schiffman, especially this chapter of fractals. As Alejandro explained, the idea of this behavior is when we have a function, we declare a function, and inside the function we call again the function, right? So this is the main goal. So graphically we can explain this in this diagram, or we can imagine when we are where we are between two mirrors and we see the image as an infinite, no? So the point is how we control how many reflections we see in order to our computer don't crash, no? So we need to make a condition to control this repetition. So my idea to doing this exercise was what happens if we have a list of points and we want to connect them, all of them in a polyline. And the first iteration, we just need to add a expression to close the polyline. So in this case, we need to add again the first point in order to close the polyline. So when we have the closed polyline, then we can find the line segments in the code, and we can use a parameter to define a point at the position in this line. So if this parameter normally calls t start from 0 to 1, so 0 is going to be the start point of the line, and the 0.5 will be the middle point, and 1 will be the end point. So after we code this we find this list of points, we can repeat the same function again, and we can build a new polygon, a new polyline. But if we want to make this again and again and again, so the approach is to make a recursive function and to control how many iterations we will going to have, and as well we can define if there is a minimum length for the segment of the polyline to stop the repetition, and in order to don't have a very small polyline that are going to crash our computer. So as well, if we move the t parameter, we are going to have different shapes, and we will see then how we can make something with that. So my proposal with this workshop is that you can download the file, and maybe you can play with this definition, and you can define something, or I will be very happy if you share with us what you can do with this definition. The other situation is when the polyline is not open, what happened, because the repetition cannot go over and over again, because we need to check when we only have 2 points to make the last line, so we need to make a condition for that. So I'm going to show you as the definition takes time to write it from scratch. I recorded a short video of the main parts of the explanation. So in the first part, what I want to show you is how we can use the t parameter when we define a line. And let me see, I can jump this part. Okay, so we have here, the goal is just we have only 2 points, and we have a line between them. How we can define in CSharp this t parameter? You can see here the expression. So there is a function in Rhino Common that calls a line object, and we can call the function point at this parameter. In this case, 0.5, we will have the midpoint. So after that, then if we have a list of points, what we should do in order to make the polyline. So the first step will be to make a function to generate the polyline. Let me jump to this part of the code. Okay, here. So we have the list of points, and we are going to input them into a CSharp component. So we need to define the data type of the variable. We define the point name for the variable, and in type hint we can choose that is a list of points. And then this is the code from the start. So we just need to make a new polyline with these points. So with that, we have the polyline, and with this condition, we add the points 0 within this 0 to close the polyline. So let me show you. We just write the code here, and we transform this code in a function, and in the function we return a polyline. So in the function with that, we have the input parameter, the list of points, and we have a Boolean variable to define if we want the polyline open or closed. And then we need to make another function to find the points for each segment. So let me show you how we do that. So here I am defining a new variable, close, a Boolean variable to define we have this option to choose if we want the polyline closed or open. So now if we pick the toggle button, we will have this behavior. Now let's jump to find to make a function to define to the list of segments of the polyline the t point. And this is the code. I can stop a little stop the video to explain you. So in this function we have a return. We are going to return the list of points, and the inputs are the first polyline and the parameter t as a double value. So then we have the list to collect all the points. First we have an empty list, and then we print just to check how many segments we find in this iteration. So in a loop we can jump to see for each segment of the line. As we know how many segments we have, we can make this function the point at for each line we found. So now what we need to do is a second function to call these two functions and to call it the function again inside. So this is the last function, the recursive function. So we will see how to do that. As we are with not too much time, I'm going to jump this. I already showed the diagrams. So in Grasshopper, normally what we do is just to copy and paste the same function again and again, but this is very difficult to handle, and the definition can be very big. So when we code this, from a point of view, it's more easy to control. So in this part, I'm going to show you how we can build this function. For that, we make a new input to define how many repetitions we want, that I call it the variable n. And here, what I decide to do is first, I declare an empty polyline to collect all the polylines at the end in the function. And in the first function that we use to make the polyline, we generate the first polyline and we add this polyline to the list. So here we don't need to call the make points at in this part. So we just need to add to the list, to the empty list, the first polyline. So this is this part of the code, and this is the input that we are going to use for our function. So we are now ready to go to see the how I define the function. Let me jump there. Okay, so here we this is the initial part, and I can stop a little bit to explain. So here we define this name polyline recursion loop, and for input we have the list, the new polyline list. We have a boolean value to decide if we want the polylines open or closed. We have any number of repetition, and we have the same parameter t. Now we can see that what we are going to do is first to call the function to see how it behaves. And then we are going to put the input, the new polyline, and just this argument. So let me jump to show you the function. okay, this is the function. So in this part we have in the first part we have the first polyline, and with this line we choose the last one. In this time we only have one polyline, so we found the polyline and we use it to define the first function to define to find the points at the parameter t. After that, we then just call the second function to make the polyline, and then we just go ahead. And then in this line, we can add the new polyline to the list. Then we define and the number of repetition we increase for one for each iteration, and then we make an array to collect all the lines of the segment of the polyline in this line. And then we need to make a condition to control the minimum length that we want. So in this for loop, we are going to define this condition, and we were going to check the length for each line and define a minimum length. So in this case, I just put a variable 0.5, but you can choose whatever you want. And then we need to make another iteration to call the function. So here we can see in this condition, if the number of repetition is bigger than 1, so we can call again the function, and we copy it here. So when we just copy this, when we call the function again, the recursion appears. So this is just what I did. And you can see in the moment I just define the argument, and I end the statement with the semicolon. Right now, the components start to work. So what is missing now is when the polyline is open, we need to make a condition to control if we have only 2 points to define the last line. So this is that I'm going to do at the end. Let me show you. So here the code is working. So you move the slider to define more repetitions, you can have it, and that's all. So take a look when I define false to have the polyline open, this situation that when we move the number of iterations, so they are going to there is a moment that the algorithm will crash. So we need to control this situation. In this part, I'm going to show you how I wrote this condition. So condition to check if we have only 2 points to make the last line. So as we have the list of segments and we have the list of points, we can just check when we have only 2. So when we have only 2, just we break the code and we return the list as we have it. So this is all. This is the end of the script, and now you can see why it stopped when you continue to move more iteration and you don't have any more because you cannot have it. And that's all. So here for to end the presentation, I just want to say thank you, and I finish with that. So this is the code that you can download, and I explain the code in parts, and this is the last part that I just showed you in the video.
Okay, thank you, Andres. Well, I think that it's my turn, right? Can I share my screen? Just 1 minute. Okay. Can you see my screen now?
Yes.
Yes. Okay. Well, basically, I'm gonna make the step before from the recursion function. Basically, I'm gonna make a nested loop, but it's gonna be based on in Python. Python is one of my favorite. Well, basically the only one that I use, but and I have a little bit. I'm still learning. So basically, I'm gonna make a walkthrough for a nested loop that I hope that you can enjoy this. So basically, I'm gonna declare my my variables, polyline, t, and n. For those who are kind of new with declaring variables inside of Python, basically here's all the variables that you can find or that you can just use as an input. In this case, we're gonna use a polyline. Here gonna be a floating number or a double in C#. And here
Salvador,
is gonna
sorry,
be
we are not seeing the code.
no.
No,
Oh.
only Rhino.
Only Rhino. Oh yes, but is Rhino and Grasshopper? Or
No, we are not seeing your Grasshopper.
okay. Sorry about that. I don't know how show Windows. And now
Okay.
you can see my Grasshopper.
Yes.
Oh, okay, thanks. So then I'm gonna declare my n component, my n variable, and it's gonna be an integer, and I'm gonna use these inputs, right? The difference, I'm gonna show you a little bit the difference between how the C#, basically how you can import your libraries. When you start using C#, basically by default you're using all these libraries, and you can add more. And here are your, as you have seen, it's just like here are your variables, and then here are your functions or definitions in Python, as you're gonna see right now. So basically the way that we can just import libraries is like this. Import, in this case, I'm gonna use the Rhino library, Rhino geometry. You can see that there is a lot of documentation right here and another files that you can import from Rhino package. It's gonna be a G, and then I'm just gonna start like making my definition. That is gonna be a poly subdivision, and I want to bring inside my initial polyline, then my repetitions, and then my T. So gonna start by making an empty list, and the output poly subdivision, polyline, and T. So I check if everything is fine, it's running. So then I just gonna make the domain from T for, it's gonna be like, gonna make that by that if statement, and if t is less than 1, gonna make this t is gonna become a floating number, and then gonna declare that also my 0 is gonna be at my floating number. 0. Okay. So then gonna just append, or in this case in C# was add, in this case gonna be append. Basically it's just add my polylines inside my empty list. So polylines append initial polyline. So be there, it's not error. And then my first polyline, it's gonna be initial point, initial polyline, and then gonna declare another variable, poly segments, initial polyline. That is gonna be the number. This is the account. This will be the number of the segments of the initial polyline. So initial polyline, it's not defined. Typo right here. Now it's running, and then I'm gonna print my segments just to check this out. Poly segments. It's running. It's 6. Basically, are these ones 1, 2, 3, 4, 5, and 6, and then gonna make a for loop for k in range 0, and is the length of our segments. Print k to understand what's happening inside of this loop. Have a typo. Segments. Repetitions. Sorry. So basically, I'm generating here my loop, and what is happening right here. Sorry, doesn't need length because it's already have an integer number. So now we have another typo. Print. Okay, right now will work. Now I have 1, 2, and 9. Okay. Now we can keep them. So if I just gonna put right 6 is okay. Okay. Now it's working. So I'm gonna declare an array. It's gonna be my segments. It's gonna declare by my first polyline. I'm gonna get the segments for this polyline. It's a method. So it's running, it's okay. And then I'm gonna make my point 3D. Done. Another for loop. That is the code, the nested loop, basically, in range.
Okay, Salvador, I see your screen frozen. I don't know the others.
Yeah,
It's
I think
frozen?
we see the other screen. We are
What
sharing
screen?
your screen at your right. This is the one we are seeing.
That's funny because I was cheating. So basically I was copying that this code. So basically, well, I'm gonna make something. I have some kind of troubles with it, with kind of trouble sharing my screen. Sorry about that.
No problem.
Now what's happening right here? Now is the same screen or which one? Is the same screen or
It's no, it's okay now.
it's okay now?
I think it's okay now.
Oh, okay. Thank you. Well, so basically, as you have seen, I was cheating. I was copying the other with my other screen. It was like, well, but it's okay. Just like it's like having a walkthrough for this nested loop, and well, I'm gonna just keep going. It's really short. I'm gonna finish right now. It's almost ready. So then we have these segments for make that empty list and just display the point inside of this curve that is just gonna show, and we can set that with the t value. Segment. Segment j point at nt. Okay. This segment is not defined. What's happening? Segment this way. I must declare here another empty list that it will call my PT segment. Now it's working. So then gonna add our first gonna add basically here the first point to close the polyline and to close the polyline. Segment my value 0. Check that everything's fine. Second poly, it's gonna be my RG. We're calling here the other library, the Rhino geometry library, and then the segment. That is gonna be the list of points to create or generate this polyline, and then polylines. Second poly. And first polyline will be my second poly, and then for not crashing my script, I'm gonna use the PT segment to clear values and then return polylines. So hopefully this gonna be okay and not crash. It's working, and this is our nested loop and output. Create curves, and it's not displaying. No. Okay. Polyline for second. I'm gonna name this one. Okay. Now it's working. So basically what is happening right here, and just what Andres and everyone what was explaining about the recursion is that the amount of repetitions. Basically, this is something that probably the iteration of the variations, it's gonna be kind of, it's gonna generate this amount of values that will be a loop inside of another loop. In this case, we make this, I like this effect, by the way, because it's generate like kind of radial, or I don't know, it's kind of cool. But basically, this is the first, for me, it helps me to really understand the first step to get the recursion function, because here you can start to visualizing that you are doing you are using basically a variable inside in another variable by doing by using by making a cycle inside of an for loop, sorry, inside in another for loop. So I think that at the beginning, just like really helped you to get this output by this empty list, and also to really understand what is happening inside of different iterations, and you can generate a multiple variations that it could be just like infinite, like fractals and other ones. So I think that um, that's it, and that's it for me. I don't know if you have any questions. I think that it's time, or I don't know, it's 4:30, but just in case if you have any questions about Python or about C#, or I can post another GitHub repo. And thank you, Dean Rose, for telling me.
The link of your GitHub and where you have the files.
Yeah, I just share this. It's a more complete. Basically, I'm still learning about how Python works. So basically, I'm trying to make a repo where you can just translate from C# to Python. Some exercises for other places like Parametric Camp, where I just met Andres, and it's kind of cool place also to just learn. And I hope that you find this useful.
Yeah, sure. Thanks.
And thank you, Dean. I didn't see your message. so my cheating screen was there before.
Well, we still got the message at the end of the presentation, so it worked out fine. Now, I had a question. I see you working in Grasshopper inside of Rhino. Do any of you work inside of Fusion 360? I guess you could do some of the same things in Fusion. It would be a little bit more complicated. You don't have that kind of graphical interface like you do with Rhino.
Autodesk has a similar tool which is called Dynamo.
Dynamo.
And it functions in similar, we could say, to Grasshopper. But honestly, I just played, I don't know, half an hour with it and never came back. But
Okay.
I know that was Autodesk response to this kind of parametric modeling. Because when you talk about parametric CAD, parametric modeling, and so on, basically you are telling that you are modeling the object, but relating the values, not with fixed values. You can say, I don't know, this rectangle is twice as tall as it is wide, for example. And if you change the width of the rectangle, the height will adjust automatically. But when you see some things like Rhino and Grasshopper, you have that kind of power in your hands. It's not maybe for like engineering stuff in the purest sense of the word, but interesting what you can do. You have also free open source tools like Blender. Blender has a plugin called Sverchok, which is like Grasshopper but in Russian, and it has more or less the same idea, but you don't have you are not anywhere close with the documentation. For Grasshopper, you have like a ton of resources, and for Sbershop, you have some, you know, Russian forums that aren't sadly very helpful. But you can try, you know, those are the tools similar to.
Okay, great, thank you.
Yeah, good to know. I will try because I just saw the prices of Rhino, and I think for just playing is a bit expensive.
Yeah, you know, you can download Rhino, and Grasshopper is included in the, I think, from version 5 and so on. And you have a 30-day trial, and then you can't save your work. It's interesting, you know, to play and so on, but you know, it's a really closed ecosystem.
Mm.
Also, I think that in Revit there is another component that is like Rhino. I don't remember, but you can export everything or import everything inside of Revit, and it's made like communication between Autodesk and like Neo, for example, and Rhino inside Revit. I think that it's called a plugin, and you can develop the same things and just export as a family, and it will work. Basically, gonna provide you also on data sheet about what you are developing inside of Revit.
Anyone has more questions?
No.
I will take that as a no. So thank you all. Thank you guys for presenting. It was, you know, really enlightening. I hope that we can do this more often, not only inside each year's FabFest, but I don't know, maybe once a month we can gather together. Please follow us in social media as the ADC. So thank you for coming. See you later.
Thank you.
Thank you.
Thank you. Thank you all.
Bye.